Hello everyone, welcome watching this video. My partner and I will introduce a framework named OJoin, which can be used in the Internet of Things. First, I will introduce the importance of the framework. Then my partner will explicitly describe OJoin framework and OJoin Lambda architecture. Later, I will present the evaluation and conclusion. Then there are references we cited. As we all know, the Internet of Things is the network of physical objects or things. With the development of IoT, the scope tends to be larger and the number of involved devices increase rapidly. Correspondingly, the IoT environment becomes more complicated because of large numbers of practical options. Thus, programming for such environment also becomes difficult. In order to solve this problem, it is necessary to implement standard frameworks to simplify programming, such that systems can be developed according to a certain style or method. Next is turn to my partner to describe OJoin framework and OJoin Lambda architecture to you.
So, I am going to tell some details about OJoin framework. And what is OJoin? OJoin is an open source API framework, which is a tool for realizing object sharing through a network. The use of APIs provides an understandable way for these software developers to work with their own projects. These APIs are functionality, so that services such as getting temperature or time are available to clients on the same network. There are two main software components, the client library and the router client library. If you are curious about why there's no server library provided in the OJoin framework, don't worry, because all OJoin applications are client of the router. From the high-level architecture perspective, two nodes are in the OJoin network. One is the router node and the other one is leaf node. As said above, all applications are client to the router, so it's not surprised that all the leaves and router nodes in this picture are clients. But who will provide services if they are all clients? Well, some of the nodes truly implement services functionality. That's why there's two-headed arrow here. This OJoin architecture forms pure session in the network. Other networks in the same broadcast domain can also be added into this network and be integrated as a larger one. To implement such client libraries, two clients are introduced. The standard client, which runs on high-level operating system environment, such as Linux and Windows. Another one is the thin client, which aims to small embedded devices with a minimum memory size, such as thermostat. When we have a brief concept on how the OJoin network architecture looks like, the next question is how devices with the Android on the network can communicate. The answer is already shown in the slide. Yes, through a software bus, D-bus. Look into the picture. First, we have two devices, host A and host B, which implement router client library. Both act as standard client in the previous slide, as devices are in pair in OJoin architecture. So let's just take host A as the client and the host B provides services functionality. First, host B will advertise the service which implements interfaces. Once a proximal client, host A finds this service, will connect to the advertiser supporting this interface, and the D-bus is established. If two networks find each other, buses will merge into one D-bus, and the devices in the same bus have one single shared namespace. However, some small embedded devices, which can only be implemented as thin clients, are impossible to run this bus daemon. Instead, they use a D-bus attachment to use the bus daemon running on the standard client. That is the reason why in the last picture, leaves cannot connect to each other. Peers can discover any applications via the D-bus, and the multicasting services become achievable. I would also like to show the basic software architecture to you. There are two Odroid software frameworks in the architecture. One is Odroid Core Framework that provides client library and router client library, which are the main components of this Odroid. With these libraries, Odroid can implement discovery connection functionality. Besides, two managements, one for connection, one for network, are included in the core framework. Another framework is to provide basic service applications, like onboarding services, which provide a way to let devices onto a network. Notification services, which inform user about the things on the Odroid network in an understandable way. And the control panel services, which delivers a user interface and controls the parameters set by users from the user interface. With Odroid's framework, it really seems to offer an easy way to connect things. However, what is the limitations? Again, scope of Internet of Things has grown extremely rapidly, and in the near future, it is not hard to imagine that all these things in the world, even human, can be connected. That raises a question whether this framework can be expanded to a large-scale environment. Pitifully, the answer is no, because this framework is not able to store and process big data, which is the main specification of the large-scale environment. That's why I would like to introduce an improvement of the Odroid framework. That is, Odroid with Lambda architecture. The Lambda architecture has two different layers to process data. One is speed layer. From its name, we can tell that speed of processing such data is fast, and this gives the users who query a real-time data view. Another layer is bench layer. It stores the master data set and is unchangeable and in constant growth. Users can also query a data view from this layer, but for the speed layer, once data in the speed layer has been forwarded to the bench layer, they are deleted. To implement this Lambda architecture, two technologies are applied: the Mango database for data storage and the Apache Storm for processing data. Let's zoom into an example. This is the basic Odroid network. To enable it to large-scale environment, the support node in Apache Storm will receive data stream and distribute data stream into some boot nodes, which are responsible for computation, and both nodes that integrated with Odroid standard client can connect the devices through D-bus, or forward the data stream to another boot node. Okay, that's all I want to talk about Odroid and Odroid Lambda architecture. My friend will give some conclusions and evaluation for this topic.
Odroid Lambda architecture can realize automatic control according to the stored data pattern and customized topologies. This makes life easier and more convenient. availability and accessibility can be achieved. All-join framework, Mongo database, and Storm are all open sources and can be achieved from the internet for free. Everyone can access to them and use them. Scalability is also obvious. For all devices with all-join application, they can join all-join network via the bus attachment. Security occurs at the application level and multiple authentication mechanisms are supported, such as PIN code. Once authenticated, all messages between two devices are encrypted. However, data privacy is a problem. In the Lambda architecture, each collected sensed data are stored in the Mongo database. They are immutable and cannot be modified or deleted. If those precise data are exploited to the third party, the privacy cannot be guaranteed. According to the previous description, all-join is a framework which can be provides communication mechanism to connected devices. However, it has no capability to support large-scale smart environment management and big data storage or analytics. This problem can be solved after integrating all-join in Lambda architecture and equipping with Mongo database and Storm systems. These are references we cited. Thank you for watching.